week we're going to be talking about business and I forgot. See, now I'm going to hate this one too. I can use this mic, and then I don't have to stay here. Okay. So this week we're going to talk about more aspects, more different ways that we can visualize model performance. Oops. Obviously, I'm not an actress, so I don't know how to do all this stuff. Okay, so last time we talked about confusion matrices. We talked about true positive rates. We talked about true negative rates, false positive rates, false negative rates. We're going to expand at that, but as I do each week, I like to discuss the fundamental concepts that your book is discussing in each of the chapters. And so we have two fundamental concepts today: visualization of model performance under various kinds of uncertainty, and further consideration of what is desired from data mining results. You may notice the second one has occurred many times because really you cannot have a data mining process, you cannot have a data mining project if you don't know what the goals are. And the goals, you should always be coming back to the goals because the goals will determine what ultimately you do. So if you do not have a question that's driving your project, then it's going to be aimless. So we don't want that to happen. So this comes up more than once. Generally, for most people, visualizations are actually easier to understand than tables of numbers. So a lot of what we've been doing so far is we've been getting tables of numbers, and as you did in your midterm, I'm sure you struggled with interpreting your tables of numbers. And so an important thing to remember is that visualization of your results is generally more meaningful to your clients, to your managers, whoever it is that you're doing the analysis for. So for example, one of the things that I've done a lot of is called survival analysis. It's not part of this course, but it's related to reliability analysis in engineering. But survival analysis is time to death. And when you're looking at time to death in any particular data set, some people leave the data set without dying. They leave before you're done with the study. Maybe they move away from the area. Maybe they change doctors and go out of your EMR. Maybe they actually get hit by a car, so they're dying of a cause other than the disease you're studying. So we call that right censoring. And we almost always express those results in survival curves that basically, well, the first kind of curve is a hazard curve. And so it shows the hazard at any given moment that someone in that group will die. That's called hazard. So it's best shown graphically. A table of charts where we just have the numbers and the probabilities is not going to be meaningful to people. But if they can see the probabilities changing across time, then they will find something meaningful in the data. Oh, you know what? I'm not doing this right because my little picture isn't in the side one. Oh, well, we'll keep going because maybe it'll work still. Okay. So it's really important to think about that. And as I always like to say about this point in the semester, is a picture is worth 1,000 words. Almost always people can relate to the pictures. It doesn't mean they're always interpreting the graphs correctly. But if you, as someone who's leading the project, can explain it well, then they have a better chance of understanding it. So let's talk about some model visualizations. If you recall last week, we dealt with confusion matrices. And then we also had sort of a cost-benefit matrix, and we talked about multiplying those two things together that enables you to come up with an expected value or an expected return at any point in, well, for any point in your data file, because you could get those values for any point in your data file. But more specifically for the whole combination, and we're going to take a look at the confusion matrix again in the next slide so we can talk about parts of that. So in a lot of data sets that we're looking at, in a lot of data mining sets, one of the things that they tend, or the types of things they tend to be worried about very frequently occur in very small numbers. So if you think about all of the numbers of credit card transactions that exist, then you will realize that it's a very small proportion of those are fraudulent. And so basically, they're searching through a haystack trying to find a little tiny needle or two within the haystack. And so that means that if the probability of having an actionable event, a probability of a 1 in a 0, 1 type of binary variable is very, very low, you can see that all the probabilities for that are going to be low. So by default, JMP will cut off at 0.5. Basically, if you have more than a 50-50 chance of being a default or a fraudulent transaction, then that will come out as be predicted as a 1, a default. But if you have less than a 50-50 chance, a probability less than 0.5, then the prediction will be 0. And so what happens when you have very rare occurrences is you come out with all zeros. So in other words, you don't get much of anything. But what we can do, rather than do that 50-50 cutoff that JMP tends to do by default, we can actually use the class probability that is predicted to order the cases from most likely to least likely. And very often in a situation like that, you'll have a budget to do your study. So for example, think about the IRS. It's tax season, so we might as well think about the IRS because that's where we all are right now. Mine are done, yes. Anyways, it's tax season, and so we think about the IRS, and they are always, or not always, but they should always be looking for tax fraud. And so if you think about how many millions of tax returns are filed each year and how few of those probably are fraudulent, it doesn't make sense to just classify each one as potentially fraudulent or not fraudulent, because probably they'll all end up being not fraudulent. So once again, if we just take that data that we have and we order it from the most likely to the least likely, then the IRS can investigate the top ones from the top down, from the most likely, and work their way down until they run out of money to do it in person. And then they have some computer ways of assessing fraudulent tax returns, and so they can go as far down as they can go in the list with that as well. So it's not that we think that the probabilities that are predicted by the models that we've been building are really true probabilities, but they certainly, their rank order of the cases will still be very good, okay? And so that can help us to analyze the data in appropriate fashion. That can help us to look at the most likely fraudulent transactions. There was a time just a few years ago when they were analyzing, it was either Medicare or Medicaid returns from a state in the New England area. And of course, I can't remember states in the New England area, but maybe New Jersey or something. In any case, they found, so you know how you have DC-9 codes? When you go to the doctor, you get like a yellow or a pink sheet afterwards, and it's got all these numbers listed on it, and the doctor checks off a few of them, and then you go pay, right? Okay, those numbers I think are called DC-9 numbers, and they're codes for different procedures, I guess. I don't know if they're codes for diseases even. They're different procedures and diseases. So then they can charge you more and more money for each one that's checked. But the idea is if you have a Medicare or a Medicaid patient and they check off those different ones, Medicare and Medicaid fraud are considered a problem in the medical field. And so what they can do is predict the probability of a subset of known cases that are either fraudulent or not, and then they can rank those probabilities and use those models then to predict additional cases. And they did this, and it reported in the New York Times, maybe, Washington Post, I don't know, something back east. And they found that there were 29 DC-9 codes that were correlated with fraudulent transactions. And then they were able to say the more of these 29 that were indicated, the higher the likelihood of fraud. And in that way, they were able to recover quite a bit of money that had been from fraudulent claims So it's very helpful, it's very useful. Even if you're not predicting at a 50-50 level, that ranking can be very helpful. So, reminding you of last week, the confusion matrix, we had true positives and we have actually positive, actually negative, predicted yes to be positive, predicted no to be not positive, thus creating true positives here. And this is the prediction, so these are truly positive and these were falsely predicted to be positive. So true positives and false positives, false negatives and true negatives. And so these are the 4 different cells that we actually have. And these different rates can be meaningful under different circumstances, but these are the cells that we can use to sort by. So to give an idea of ranking classifications, here's a visual example. So you see that we might start, okay, so I should point out that score in this case is the predicted probability. Okay, so the predicted probability of being 1. So in the first case, everybody's classified as 0, and then we move down 1 in order of the scores. We move down 1, and we see the first one was positive, and we said yes, and so we ended up with 1 true positive and 99. Okay, now are these in the opposite direction of my other ones? Because I made it match jump. I have to look and see. Because I have to remember what yes and no is. For some reason I forget. Yes is what we're predicting. So these were predicted to be positive, and these were actually positive. So we have 1 true positive and 99 false negatives. Okay? And that's fine. So far, so good. So we move down 1 more ranking, and indeed, that one was positive again. So we increased that. But then on our third one, it was predicted to be positive, but it was actually negative, and so now we have 1 here. So you see what we're essentially doing is for every step down the rankings, we are creating a new confusion matrix, which we can then multiply by our cost-benefit matrix, and ultimately decide where does it go from being positive to negative if we have that much budget, or how far down can we act, whether it's looking for true fraud or whatever our action is, how far down can we act in the budget, within the budget we have. So that's how we can use those confusion matrices to actually do a ranking. And what we're doing is we're not actually splitting at 0.5. Instead, we're just moving down 1 step at a time and seeing how the confusion matrix changes.
I didn't see the 2 on the third.
Because the next one was a negative. So when we move down on the third, and then it shows, well, if we went this far down on this baby data set, we correctly identified 6 positives. Sorry. We correctly identified 6 positives, but we thought that 4 negatives were positive, and so on. And we're still working our way through to the larger numbers on the bottom. Okay? So actually, in any particular project, like a project that you might do for this class, you really have to think about what's worse, the false negatives or the false positives, and use that in evaluating which of your models to use. If you have a model where you have a yes-no target variable, a binary target variable, you really have to think about the confusion matrices, and then you have to think which is worse, false positives or false negatives, and use that to help you evaluate rather than the strict accuracy rate. And we've talked about why that oversimplifies the situation in the past. So, one thing we can do then, remember how we had our cost-benefit matrix that we could multiply for expected values last week? Well, we can take each one of these places where we made a cutoff and then multiply it by the cost-benefit matrix. And as I said, that can enable us to make the decision about where we go from spending, where we go from making money by investigating more cases to where we start losing money. And so this is obviously all something that has to be done iteratively. It's not something we can just sit down and do, with a Excel spreadsheet and not have it automated in some way. So it is something that would have to be done iteratively. But we can go ahead and do that to make a decision about where we actually want to make the cutoff if we're not going to make it at 50-50. And if we're going to rank the cases and we don't have enough money to check everybody that is classified as positive or potentially positive. So when we take each one of those new confusion matrices and multiply it by the cost-benefit matrix to get the expected value, then that is actually our expected profit, is one way we can look at it. And so that can determine how far down we're going to go. And as I've already pointed out, budgets can be limitations. You may not even be able to go near as far down as you would like to. And sometimes that's not a limitation. But when we compare models, that's what we have to think about. Which one is going to give us the best profit? So here's an example of a profit curve. Remembering that we can only create profit curves if we have that well-defined cost-benefit matrix that we talked about last week, where it's what is the cost of a false negative or a false positive, but what is the benefit of a true positive. So we have to multiply those out across that matrices. So here's an example of what a profit curve might look like. And we have basically looked at two types of classifiers, logistic regression and classification trees. They're using three. I'm not sure. I think the third one might be a naive Bayes model. We are only learning two for continuous target variables and two for binary target variables, but just know that those are not the only things that exist in the world of knowledge discovery, predictive analytics, and data mining. So, in this scenario, looking at this example, in this scenario they say, well, let's say we have 1,000 customers and you target only those classified in the yes category. So those who are below your cutoff is of $0. And then they give this example. What if the cost of targeting is $5 and each accepted offer grosses $9 with an expected profit of $4 for each accepted offer? Thus, the true positives result in a $4 profit. This is really an oversimplified example. But in this situation, they've built three classifiers. Let's just say that one of them is our logistic regression, one of them is a classification tree, and the third one could be a naive Bayes, it could be a support vector machine, it could be a neural network, whatever. So what we're seeing is what percentage of instances are we going to target with our $5? Or if we were looking for Medicare fraud, what percentage of the Medicare cases would we be looking at? And these are different cutoffs. You can go from 0 all the way to 100%. And for each of these different cutoffs, you can expect a profit or a loss, depending on that calculation of expected value that we talked about last week. So here is classifier 1. 0, by the way, of course, is where you break even. Anything above 0 is a profit. Below 0 is a loss. So here we are going up and up and up and up and up. And on that curve, we would maximize the profit. Looks like it's about 55%. On the other hand, if you look at classifier 2, it does worse than classifier 1 initially at different cutoffs, but then as we get larger and larger, it surpasses the profit of the classifier 1. So if we had an unlimited budget, we would probably go for classifier 2 and cut off where the max profit is. If, on the other hand, we had a budget that only allowed us to look at 8%, we would go with classifier 1 because it does better than classifier 2. So a profit curve is a way of taking a confusion matrix in combination with a cost-benefit matrix and deriving a profit where it's good to cut off. Okay? So that's a profit curve. Don't worry, I'm not going to ask you to make one. It's just one way to visualize data. So there are really two critical conditions that have to exist in order for you to have a profit curve. You have to know what your class priors are, and that is, in your overall data set, what proportion of positives and negatives do you actually have? What percentage of zeros and ones are there actually in the entire data set? And in addition, you have to have a nicely developed cost-benefit matrix, and that's the hard part. And that's the part that's hardest to come up with. We can usually get the rest. But you would really need to have both of these in order to start drawing profit curves. And some of the problems, if you think about fraud, fraud changes at different times of the year. There's different times of years when there's higher fraud or lower fraud. If you think about fraud in terms of location, different regions of the country will have different rates of fraud. So this is really going to be very location and time specific. So it can be very, very difficult to develop that cost-benefit matrix. So profit curves, they're really cool in concept, but they're a lot harder to implement than you might think, unless you have really good data about how that's going to behave. So in reality, you often don't know these things, especially that cost-benefit matrix. So what happened? How could that be? Slide 8's in there twice for some reason. I don't know why it's doing that. Okay, so what if the costs and benefits are not known? Well, there's this wonderful thing called a receiver operating characteristic. Sometimes it's called a graph, sometimes it's called a curve. And it actually helps us to understand how well our model is behaving. And the thing that I love about this is where it came from. It came from World War II ham operators. I may have mentioned to you before, that's where I get the signal and noise idea. Well, these were developed by those kind of operators, those radio listeners who were talking about when they could really hear something or not hear something. And so what's classified as a signal or not a signal. And so they developed receiver. That's why it's receiver operating characteristic curve. It's based on receiving radio signals. So, but we think of it as just correctly identifying true positives and true negatives. So what it does is it incorporates both the concept of a true positive and a true negative because of the relationship between false positives and false negatives. The two things have to add up to one, so I only need one of each pair. So what they do in an operating characteristic curve is they do a true positive rate and a false positive rate. And the ROC curve plots the true positive rate on the y-axis and the false positive rate on the x-axis. Okay. Looks like this. So a curve that cannot distinguish between the signal and the noise will simply be the diagonal line that you see. And if you randomly classify, theoretically you should be able to do as well as that diagonal line. If you are able to correctly classify things, you're going to be up above that line. And if you do better than random, you'll be above the line. If you do worse than random, you would be below the line. So hopefully we'll never have a model that puts you below that diagonal line, because that means that you're doing worse than a random classifier. So theoretically, the random classifier should do as well as that horizontal line. And the best place to be is in the upper left-hand corner, because in the upper left-hand corner, your false positive rate is 0. That's a good thing. You want your false positive rate to be 0, but also your true positive rate is 1. So if you're in the upper left-hand corner, you're doing basically a perfect job. So that's a good place to be. So if we look at these three classifiers, A, B, and C, or these three cutoff points, whatever it was based on, the one that gets closer to that upper left-hand corner would be the best one. Now, these ROC curves, as you can imagine, if you were to show them to someone cold, and perhaps even me showing to them them to you right now, you may feel these are not very communicative to you. So we actually do, let me make sure I'm in the right place. Now here we're talking, first I have to talk about generating these curves. But one thing I do want to say is that there is a shorthand number that expresses this curve, and it's called the area under the curve. And it is simply the area below the curve that's created when you think about your classifiers. So, okay. So, how do you generate the ROC curve? The first thing you have to do is you start, as I showed you earlier, with ordering all of your cases in your database, all of the cases in your data file, from the most likely to the least likely. That's the first step. And then you start with some kind of cutoff. So initially your cutoff is going to equal the maximum. But then you move down the classifier, and at each step you count the number of true positives and the false positives, and that's how you actually construct your curve. And luckily for you, JEMP makes ROC curves. So you never have to do it this way. But it's nice to understand how you do it. Here's a visualization of how that works. We go back to that picture we started with, and in this case it went from, I don't know why they turned it upside down, but you can see at each point you get a different confusion matrix, which leads to a different false positive rate and a different true positive rate. And from that, you can construct it each one step down your data set. One case at a time, one instant at a time, you move through the data set and classify it. And that's how you create your ROC curve. But as I said, JEMP's going to do that. So the nice thing about ROC curves are very nice because they do a number of things that make them very useful across different situations. And so the first thing is that it decouples classifier performance from the conditions under which the classifiers will be used. And most specifically, it's independent of the cost and benefits, but it's also independent of the proportion in the true set, in the true data set of the proportion of yeses, the proportion of actionable events. So it decouples that because most other evaluations are dependent on the proportion of true positives or the proportion of actual positives in the data set. So that can make it very difficult. And it's also not going to be influenced by cost benefits, so we don't need the accountants. That was one of my accountant jokes. Anyways, I hate it when I have to tell you guys when I made a joke. Really? Okay, so it's not the most intuitive visualization, and so because of that, we've developed a number that helps us to understand that, and we call that number the AUC, which I thought looked like the word auk. And so guess what that's a picture of? It's an auk. An auk is a kind of a bird. So anyways, AUC is the area under the curve. So imagine if your area under the curve is 50%, you're right at random classification. If you have an area under the curve less than 50%, well, you've done worse than random. And that means that's a super bad model, which is why my little distribution of rough rule of thumb, that it took me a while to find a rough rule of thumb to share with you guys, but I got this off a website, which I hopefully cited, of course. Oh no, I cited the picture of the auk. That's pretty funny. Oh yes, I did cite this general rule of thumb from this particular website. In any case, this is 0.5 is random guessing, 0.5 to 0.6. Sometimes people say the model failed. In big data with small positive rates, if you can get to 0.6, you've done pretty well. But the rule of thumb says your model failed. 0.6 to 0.7, the result is poor, fair, good, and excellent as we move up. So that is just a rule of thumb. It is not hard and fast. As I said, if you have a very large data set and a very weak signal, you're lucky to get in the 0.6 range. And that's what my experience has been. Because that ROC curve, which is so difficult for people to understand, there are also a couple of other curves that I will mention, and I can't remember which ones. I know that JMP does lift curves. I can't remember if they do cumulative response curves. But the cumulative response curves and the lift curves are two other ways of representing data. Sometimes I have found, personally, that when I'm working with clients, they can relate to a cumulative response curve better than either a lift curve, because a lift curve does have its own quirks, and better than an ROC curve. But it's not really considered the best way to represent the data. But it is a way, and if it helps people understand what you're trying to tell them, then that's a good thing. So again, it's a curve, so you're going to have a y-axis and an x-axis. On the y-axis for the cumulative response curve, you're going to get your true positive rate. So that should consistently go up and up and up and up. You'll get an increase the more you classify as positive. And the percentage of the population targeted is on the x-axis. So as you move through and I have a picture I think on the next slide, as you move through, ultimately that's going to go to 1, because if you classify everything as positive, then you'll classify everything that's positive as positive, right? Say that really fast 3 times. Okay, so once again, the diagonal line will represent your random guessing. And this is the weird thing, and this is why lift curves look so weird, is the lift curve is the value of the cumulative response curve divided by the diagonal line. So if you're at 1, you're doing just what the diagonal line would do, which is random guessing. So you want to have a number greater than 1. And so let's look at what the cumulative response curve looks like. So in the cumulative response curve, as I said, the percentage of the instances which are being classified as yes go along the horizontal axis, and then the vertical axis is the percentage of positives. So these are classified as positive, and these are the true positives that you have up here. So the blue line, diagonal line, once again, represents random guessing. So if I make my cutoff for calling something positive at 20%, then you see I have these two classifiers, A and D, are at about the same place. Then we go to C, and then we go to B. But as we move along in more and more instances, then we see that, well, it kind of looks like D is pretty good all along, although A and D are sort of tracking each other pretty well. Not perfectly, but they would both be very good classifiers depending on where you were going to cut off. In general, you're not going to go all the way to 100%. So let's look at a lift curve. Now remember, in the lift curve, we're dividing the number that's being classified up here, this percentage here of positive targeted, we're dividing that number by this number. So you can see if I divide one of these numbers by this number, it's going to look really big. But as this number gets bigger, its bigger distances are going to look smaller. Okay? So that's why the lift curve is a little bit confusing. And so one way to think about that is that the lift is how much higher the cumulative response curve is above the diagonal line. So let's look at a lift curve. Oops. Okay. So remember how I said that when your denominator is really small, it's going to make the whole number look big. So what happens is by having any model, we lift a lot. So this is like no model, so then we have a model and we lift a lot. And then the more we try to classify, the worse our lift gets over random guessing. So that's the way the lift curve. It's much harder, I think, to look at and to describe to people than specifically than the cumulative response curve. I think that's the most intuitive of the 3 curves I introduced to you today. But the lift curve does enable you to compare different models pretty well. So let's go back to the actual process that we started with. So remember, in the process, we have business understanding, data preparation, which I hope you're all enjoying right now, data modeling, and finally evaluation. So these curves fall into the evaluation category. So that's the category that we're in right now. So if we think about the churn example that we talked about before, and we incorporate the train, validate, test that we've also talked about before, then we can start looking at an evaluation of a specific data set. So let's go looking at our churn example. And here they talk about 4 different classifiers, 2 of which we learned, the classification tree and the logistic regression. And then there's something called k-nearest neighbors, and then there's also something called naive Bayes, neither of which we're going to cover. But there are just additional classifiers in the same line, in the same vein, that our trees and our logistic regressions are. So the interesting thing about this is if we look at the model and the accuracy of the model, just plain accuracy, which we know can be misleading because if you've got a lot of negatives and classify everything as negative, you're doing pretty well. But this is all based on the same data set. And I think in our churn example, we maybe had 20% that churned. So let's keep that in mind. That's probably what we have here. So the classification tree was 95% accurate. The logistic regression was 93% accurate. This is in the training set. Remember, this should be maximized in the training set. 100% for k-nearest neighbors. And so it looks, when you first look at the training set, if all we had was the training set, if we didn't do train, validate, test, then we would say, whoa, I'm going with k-nearest neighbors because that's such a good classifier. But now let's take a step back, and instead of just looking at that, let's run it through an ROC curve, ROC curve, and just get the area under the curve, which again is an accuracy measure. And now what we see is if we do this for multiple test sets, remember when we talked about, on the same week that we talked about train, validate, test, we also talked about cross-validation, and I said we could cross-validate 5 times, or gave you an example of 10 times cross-validation. So that enables us to get an estimate of the error in our classification. So that's what this plus and minus is based on. It's based on having done multiple splits in the data set. And so now when we look at this, we see that if we average across the testing sets, if we're talking about pure accuracy, we see, again, naive Bayes is the loser. But on the other hand, if we look at the area under the curve, which is independent of the rate of positives in the original data set, then it makes it easier for us to see maybe the naive Bayes was the best predictor all along, because this is just looking at overall accuracy, which is impacted by the proportion of ones or successes or actionable events, whatever you want to call them. That's impacted by the proportion of positive, true positive, or the proportion of positives in the data set, whereas the area under the curve is independent of that. So this is probably a better evaluation over here, which would lead us to the one that appeared to be the least successful. Okay? So that's one thing to keep in mind when you're doing evaluation, is the weakness of pure accuracy. So here's a naive Bayes confusion matrix and a k-nearest neighbors confusion matrix from this same data set, from what we're talking about here in a validation set. And what you're seeing is that in the naive Bayes, we're getting 127 or 3% true positives and 75% true negatives. Here, we're just getting a whole lot more true negatives. And that might not be what we want in the data set. So the k-nearest neighbors rarely predicts churn, and because churn is rare in the data set, it gets a very high accuracy rate. But when we take into account both kinds of things, true positive, false positives and false negatives, true positives and true negatives, the naive Bayes actually makes more mistakes overall, but it identifies more churns. It identifies more of the true positives. And that might very well be what we want to do, is identify more of the true positives. Think about it in terms of disease. You want to identify more true positives, even though you know you'll have more false positives. Okay. Now to look at a graphical representation of this. This is oftentimes, by the way, what it looks like. It looks like we're barely breaking better than random. We barely do. And so you can see that this one, sometimes I have a hard time telling which one is which. This one appears to be the KNN, K nearest neighbors. The naive Bayes has the biggest ROC area, and it's the dotted line, because see how it goes up like that? So it did better. And of course, random is our diagonal. So this is the graphical representation, but I think you got a lot from the number, the area under the curve, or the awk. I don't think anybody calls it an awk but me, but it looks so much like that name. And once again, looking at the lift curve, initially the tree gives us the best lift, but as we go to a larger portion of the instances, then we find that the naive Bayes goes above the tree. So again, different circumstances, different graphical representations. Let's look at the profit curve. Again, you see the tree for small portions is best, then the naive Bayes takes over. And this curve was derived using certain assumptions. You can read it all in the book, or you can read it in my notes here, where I have told you the conditions. And then, so that was that profit curve. So in this situation, the cost per offer was $3 and the profit was $27. So in order to maximize profits, you'd probably make a cut at around 20% of targeting, 20% of the population. But now here, they've changed the instances. They've changed the scenario. So here, the proper place to cut off is more like at 35%. And that's right, you can't see my cursor. So you can see that's going to be more like right in here, where the highest profit occurs. So in summary, I'm sure I didn't convince any of you that any of these graphs were that interesting. But if you practice looking at them, really and truly, it does take practice to look at these curves. I think the profit curves are the easiest to understand. I think ROC are easier to understand than people realize, but certainly the AUC is a good way to do the trade-offs between, it does the trade-off between false positives and false negatives, rather than pure true accuracy. So it's critical to properly evaluate your models. It's critical to convey this model evaluation to your stakeholders, and visualization can help you do this, so it's a very important task to think about. A lot of what I learn at the meetings are these new interactive graphics that people are using to communicate the results of a big data mining process. So visualization is really important. I wish we had more classes in visualization. The training sample does not have to be representative, and what this is talking about is if I can, even though my training sample isn't representative, if I build my model and I can create a good order from that, even though it may not have been representative, when I put new data in, the order is still going to be good. So it may not be yes or no, this is a positive, but it may still give me a good order of which ones to evaluate, like for fraud or defaulting or whatever actionable item I'm looking for. And when information is available on costs and benefits, a profit curve is a great way to communicate. It's just that that's not always the case. They're easy to understand. Sometimes cost and benefits, though, are unknown. So the cumulative response, sometimes lift graphs can be useful, but the ROC curves are hard to interpret, but they're free of the operating conditions, so that is their big advantage. And if you use area under the curve, people can understand what you're talking about. So that is all that I have for you today, other than this lovely picture of my bicycle.